Hello, everyone. We're the UChicago Library project for spring quarter, consisting of myself, Emily, and Ricardo. The library faces growing pressure to manage its expanding physical collections efficiently, as their book collection increases in size by about 1.4% every year. For context, that's over 80,000 new books annually. However, the library is running out of space to physically store things on campus. Due to the high growth of the library's physical collections, they hope to optimize the storage and accessibility of their collections. The project will prioritize identifying which materials should be relocated to offsite storage without sacrificing accessibility for students, and also considering external factors like how events, such as elections or the acquisition of electronic copies, might affect usage. Our problem statement is, given data on the library's collections, how can we better understand the items that the university has, and what attributes of this data can help us determine which volume should be relocated to offsite storage? The final deliverable we're working towards is a proposal of which volume should be moved to offsite storage. The library also indicated that our process to deliver this proposal could be useful as a reusable tool or dashboard. In order to determine which books should be relocated offsite, we have a pipeline consisting of four main steps: data processing, subject labeling, feature extraction, and weights and scoring. After pre processing raw data about our collections as well as usage data, we group books into clusters and label these subjects. Then we extract features such as the number of duplicates that are useful for assigning a score to each book. This importance score is based on the weights assigned to each feature, determining its importance. Using this score, we can create a threshold based on how many books the library wants to relocate to offsite storage. Next, I'll pass it off to Emily to talk more about the work that we did in this quarter.
In previous quarters, the steps in this pipeline were run entirely on local machines, with each step shown on the right being disjoint, and the whole process took quite a long time. This quarter, we ran the pipeline on the DSI cluster instead of local machines, and also began the process of refining weights through both qualitative and quantitative feedback. This involved discussions with the UChicago Library about prioritizing features and developing new features, and quantitatively by exploring weight sensitivity algorithms, which examine how much the final score would change if we were to change the weight or contribution of each feature that goes into determining the score. The first step of our pipeline, data processing, involves unzipping files, converting to a file type suitable for large data, Parquet, and combining many files into one based on collections type, which is either electronic or physical. The main challenges with this step were a lack of clear documentation and incorrect file paths. Therefore, a focus this quarter was making the data processing step more transparent and reproducible. In order to achieve this, we set up a project folder on a DSI cluster for data sharing. This makes raw input data and process data accessible to all team members. We also added clear documentation of the input and output files to expect before and after each step of the pipeline. For the second step, subject labeling, we first cluster books into broad categories, since identifying similar books enables us to make recommendations about records that do not have usage data, based on known patterns for a group of subjects that do have usage data. We use the k-means clustering algorithm to separate books into 20 clusters, with each cluster being labeled using latent Dirichlet allocation, also known as LDA. This most frequently arises in cluster labels of the top subjects present within a given cluster. This quarter, we improved this part of the pipeline by speeding up the runtime of the LDA model. This was accomplished by running the model using GPU instead of CPU. This graph, shown here, shows the 20 most common subjects in one cluster labeled music, piano, songs by our LDA model. On the x-axis, we can see the frequency in cluster, with the y-axis denoting subjects. So, for instance, we can see for the music subject that we have almost 50,000 books with this subject present in the cluster. We can see that the labels for the cluster are corresponding to some of the most frequent subject labels within the cluster, with music and scores and piano music being the top three. For the third step, feature extraction, in previous quarters, they developed a part of the pipeline to clean, combine, and perform operations on existing data to get features that would be useful for determining if a book should be kept on site. Some of these features include number of checkouts, whether a book has an electronic copy, and the number of duplicates that a given book has. This quarter, we had to fix some bugs in order to get the code to fully run, and in order to make this step more robust to future changes, we created save checkpoints that save intermediate files. This prevents errors within the process from requiring the whole pipeline to be restarted, saving time and allowing for faster future development as more changes are made. Now I'll pass it off to Sean, who will discuss weighting and scoring.
The final step of our pipeline is weighting and scoring, where each book is given a numerical score that determines how important it is to keep on site. Currently, the score is given by a weighted sum of the extracted features, which in previous quarters were only assigned initially. This quarter, we set up foundations for analyzing the scoring algorithm sensitivity to weights and modifying these weights using the R package CoinR. CoinR allows us to test different weights and see the impact of uncertainty in weights on the final score. It's a convenient way to modify data, change weights, and add or remove features after the pipeline cleans and extracts features of interest. We also receive qualitative feedback from the library on features data quality and importance when deciding to keep items on site so that our assigned weights align directionally with the library's domain knowledge. I'll hand it off to Ricardo to elaborate on some of the feedback we got from the library about our features and their weights. In short, the library commented that the features, whether a book has an electronic copy, cluster performance, uniqueness, and the number of checkouts would make the most sense to weigh heavily.
One feature the library recommended we include was the cluster performance metric, which measures the performance of each cluster relative to the performance of the entire collection. For example, books in Cluster 8, containing subjects like periodicals, science, and philosophy, are projected to be checked out at a lower rate than the entire collection in the upcoming quarter, while books in Cluster 7, containing subjects like history and war, are projected to be checked out at a higher rate than the rest of the collection. Because cluster performance is normalized using each cluster's size and centered around the total collection's checkout rate, the numbers on the y-axis tell you the expected checkouts per book. That is, for Cluster 6, with labels history, literature, art, for every 100,000 books, we expect about 15 more checkouts per quarter relative to the baseline. Simultaneously, one feature they recommended we modify was the publication year feature. With the library's guidance, we are in the process of incorporating the publication year into the number of checkouts feature to avoid penalizing books that were recently published and haven't had the chance to be checked out yet. Here you can see the distribution of publication years from 1990 to 2025. Because we presented visualizations and summary statistics for all our features, we were able to incorporate the library's valuable insights. This work contributes to a replicable pipeline for library data analysis, spanning processing, subject labeling, and usage prediction. One key improvement is the addition of pipeline checkpoints and error logging, which makes the process more robust and maintainable. We've also introduced a method for refining feature weights through both sensitivity analysis and direct feedback from library staff, ensuring the model aligns with domain expertise. Importantly, this lays the groundwork for a reusable decision support tool to help libraries determine what items to keep on-site versus off-site. Looking ahead, there are several priorities. First, we plan to revisit our clustering method to improve the interpretability of subject labels. This may involve filtering out non-topical keywords, reducing the number of unclustered items, or incorporating enriched data like chapter and section titles to augment the keywords used in clustering. In this graph, you can see the top LDA subjects in each cluster, as well as the size of each cluster. The largest cluster is labeled Science, Political, Library, and contains over 900,000 books, while the smallest cluster with labels Services, Languages, General barely clears 100,000 books. One issue we ran into was words like periodicals, science, and languages appearing in multiple clusters and making the distinctions between clusters less clear. Continuing on with our next steps, we'll continue to refine feature weights using a combination of sensitivity analysis and library staff input. Finally, we aim to develop a reusable dashboard that allows staff to tweak weights and directly explore subject-level insights, turning this pipeline into an interactive and adaptable tool. Thanks for listening.